Okay, so good afternoon, everybody. We are back to the seminar version of our seminars. Today, Laura couldn't come, but we really wanted to her to talk about her projects. So she's here virtually, and although Laura doesn't need introduction from any of us, anyways, let me briefly introduce our speaker today. Laura is a senior researcher in astronomical technologies, which is primo ricercatore, anzi primo tecnologo in Italian, and at the INAF-OAS in Bologna since 2024. She got her PhD at the University of Bologna in 2006 with the supervision of Marano and Diolaidi. And she got several positions around, and since 2017, she's visiting scientist at the Institute of Planetology and Astrophysics in Grenoble, France. Her research focuses on the development of optical and infrared instrumentation and advanced technologies for astrophysics, with emphasis on AO systems. Her main projects involve update and maintenance of Starfinder, and that's the topic of today's talk. SAXO, the second stage AO system for Sphere at VLT, and PCS research and development activities. PCS is a planet finder for ELT, and today Laura will talk about why the PSF matters in AO imaging for stellar fields and how to deal with it. So, Laura, thanks again for accepting the invitation. I'll give you the 45 minutes, 5 minutes in advance. I'll give you notice.
Okay, thank you for the introduction. I think, do you see my screen?
Yeah.
Yes. And you see also the, okay. So I have to put somewhere else my vision. So you see my full screen, yes? Do I have many screens? Okay. Yeah. So good afternoon, and thank you for the introduction. And sorry if I couldn't come. I have a surgery tomorrow, and this was not really known before. So today I will talk about why the PSF is such a critical ingredient when working with high-resolution imaging, and in particular with adaptive optics data of stellar fields. So not all the kind of adaptive optics data, only it is more concentrated on stellar fields. Okay, does it work? Yes. So the point, the idea is to make a very, very didactic talk. So I'm sorry for people that know already everything, but really the idea is to make a sort of journey with the light, starting from the star and arriving to the focal plane. So really at the beginning, the PSF described how an imaging system responds to an ideal point source. And in astronomy, stars are often good approximation of point source, so we can consider as a point source. So the PSF tells us how the combined effects of the telescope, the instrument, and atmospheric shape the observed image of a star. So even in the simplest case, when we consider a perfect optical system with a circular aperture, the diffraction sets the fundamental limit to the image quality. So the diffraction is a direct consequence of the wave nature of light and arises whenever light encounters an obstacle or a finite aperture, like a telescope. So as a result, instead of forming a perfect point, the image of a point source is spread into a characteristic pattern of alternating bright and dark regions produced by interference effects. So for a circular aperture, you can say here, like you see my mouse? Yes or not? Not here, maybe?
Yeah, I do, yes.
Okay, perfect. So for a circular aperture, this pattern is known as the iridesque, and it consists of a central bright core containing about 84% of the light that is then surrounded by concentric rings. The peak width, the full little maximum, depends linearly on the observed wave, on the wavelength, and inversely on the telescope diameter. So this characteristic scale defines the diffraction limit of the instrument and sets its resolving power, that is, its ability to distinguish two closely spaced point source. And this is established by the Rayleigh criterion. So 2 point sources are resolved when their separation is comparable to the diffraction limited, so that the peak, and you can see here, the peak of the Airy pattern falls on the first minimum of the other. This is the reason why large telescopes are crucial. So a larger diameter increases both the light power, of course, and the angular resolution that allow us to observe fainter and more distant objects in greater details. So here I put a few examples of 2 sources of the same size and with a different distance, one to each other. Here we see the Rayleigh criterion, and then we see that if the distance is smaller, the angular distance is smaller, you barely distinguish that is an elongated source, but this is not resolved, and then you can see clearly the 2 sources when the angle is higher. And then another experiment that is very didactic, in which I keep the same distance between the 2 sources, the 2 identical sources, but I increase the aperture, and then I animate the thing. And then, of course, you see that as the bigger the aperture, the higher is the resolution, and my capacity, my ability to resolve the details of the image. This is just a little game, a little play that, if you have your telephone, I have forgot to tell you, you can use it to scan this QR code. This is a small game that I do with students of high school to explain them how important is also the shape of the aperture. So the light passes through an aperture, even in absence of aberrations, of atmosphere, of everything, just because of the aperture and the diffraction. This is imprinted in the PSF. So also the shape of the aperture of my telescope is appears then after into the PSF structures. So the game was to choose which was the aperture that was producing this kind of diffraction pattern on the focal plane. And of course, you know, because you are astronomers, so you know that this is the typical PSF of the James Webb Space Telescope. So this was the answer, in which you have all the diffraction pattern produced by each of these 3 different apertures. And you can see that these structures a little bit mimic or the structure of the spirals, and then it depends also if the mirror is full or is segmented with which shape has each segment, and so on. Then you can recognize maybe the shape of the pupils. They appertain to 3 very well-known telescopes, big telescopes. So if you want to play this game, you just have to try by flashing the QR code. So just going on, let's add other ingredients. So the idea is like to go through a recipe and see how the PSF is formed, petit à petit, how we say in French. So real optical systems are affected also by aberrations. Such as the defocus, the astigmatism, the coma, and whatever you can think about. This is because an optical system is a real system, is aligned, or there are small misalignment, and also the surfaces are produced by producers. There are smaller errors everywhere. So the aberrations also modify the ideal diffraction pattern and introduce additional structure to the PSF. So in this slide, I try to show 2 complementary representations of the same physical quantity, that is the propagation of light through an optical system. The top panel shows the wavefront at the system entrance. The system entrance is represented just by a circle. So it's like we are looking at the entrance of the telescope. That is a simple, we didn't put any secondary mirror or whatever. It's a simple circle. And intuitively, the wavefront describes how much the optical path deviates from a perfectly flat reference surface. So here is the example of the perfectly flat wavefront that translates in the perfect iris disk that we have seen. And then if you have aberration, this translates into the PSF, and you can see on this panel how it translates on the focal plane. So you have that, in fact, each aberration, so aberrations in some way enters into the PSF shapes. So they degrade the PSF quality. And how do we quantify this degradation between with a quantity that is called the Stress ratio? And then you will, if you are an optician, but also if you work with adaptive optics images, you have already heard about it. But it's not only specific for adaptive optics. In general, it defines the optical quality of the system, and it is a ratio. It is the ratio between the peak of the diffraction-limited perfect image and the aberrated image. So here I put an example with a diffraction-limited image, and I add some spherical aberration. And then here you can see the profile of the PSF, and you can see that the peak in the case of the aberrated PSF is lower because part of the light is spread into the halo. And so this ratio gives you an idea of the performance of the system. So the maximum is 1. When the Stress ratio is 1, it means that you have a perfect PSF, diffraction-limited PSF. And then when you have a lower number, it means that some aberration or some other effect goes into the system. Now let's do the last step, that the last ingredient in this complex recipe, that is the turbulence. So real optical systems on the ground, on the Earth, are affected also by the atmosphere. What we are looking here in this slide is a representation of the instantaneous wavefront phase as it is distorted by the atmospheric turbulence. So this is really how is the wavefront due to the turbulence. The structures are much more complex than the one that you have seen in the previous slides, okay? And the alternating bright and dark regions that you see here correspond to spatial variations of the optical phase introduced by turbulent layers in the atmosphere. So the atmosphere can be thought of as a continuously evolving medium made of cells with slightly different refractive indices caused by local temperature and density fluctuations. So this causes a fluctuation on the refractive index. As the cells move across the line of sight, they locally deviate the propagation of the incoming light, introducing phase distortions in the wavefront. So when such a wavefront propagates through the telescope aperture, it produces an instantaneous image that is no longer a smooth diffraction pattern, as we have seen before, but a complex interface pattern made of bright, you can see it here, made of bright and dark spots that are called speckles, and which typical size is the diffraction limit. So instead of having one PSF, the iris disk with a peak with the width of the diffraction limit, you have a sort of speckle pattern with each of these bright points have this size, but they are distributed on a surface that is the size of the seeing, that is much larger of the diffraction pattern. So, so what happens if the atmosphere evolves? Here I made a small video in which you see here the phase introduced by the atmosphere evolving in time. So I let it go, and then I start also the PSF. So here you see the instantaneous PSF that you have seen in the previous slide with speckles moving, boiling onto the surface. And then when you integrate, because this you do when you make images on the focal plane, you integrate. So what happens is that the final PSF is smoothed, so you lose the information on the single speckles, and finally you have a bigger and smoother PSF that is much larger than the initial diffraction-limited PSF. This example has been done with a normal, I have simulated an atmosphere of the VLT telescope, And this is in an 8-meter telescope. So this would be the ideal PSF width, and this is the real one due to the atmosphere. And the shape, and if we go to analyze the shape of this smooth PSF, and you see that is well represented by a distribution that is called Moffat, very similar to a Gaussian, but with a different description of the wings. So it is very similar to a Moffat function, and with a full result maximum that is the seeing angle. So what can we do to solve this problem? So if we want to build big instruments and have and take advantage from the angular resolution, we have two possibilities. We put them in the space, but big telescopes we have limitations, economical and technological, or we can use adaptive optics. So if I have a small video, because I don't want to enter into detail, almost all of you knows how it works, adaptive optics. So it uses the light from a reference source that can be natural, can be laser, and through a wavefront sensor, it analyzes in real time the wavefront due to the atmosphere. So it uses a system of a complex control system in order then to send commands to a deformable mirror that is on the path of the light, and in real time it is able to correct the deformated wavefront and to correct the image finally. So you try to retrieve the diffraction limit PSF, starting from the PSF that we have seen before. Which are the limits of this system? Of course, you have seen that the deformable mirror has actuators that moves behind the surface and that try to follow the atmosphere, but the measurement could be not accurate enough because the light of the reference source could be not enough, or the number of actuators is usually a finite number of actuators, and the atmosphere is a continuous variation. So there is a discretization error, and then also the atmosphere evolves very quickly in the order of magnitude in time variation is milliseconds, and also the adaptive optics system has this kind of frequency, but you have always a sort of delay because you can't apply immediately. So all these errors, I just skipped to this, translates into a not perfectly, and not a PSF that is really the diffraction limit PSF that you would like to obtain, but a sort of mix PSF between the single limited one and the diffraction limit PSF. How much is well corrected is told by the famous trend ratio that we have before introduced. So a system that is working very well try to have a trend ratio very close to 1. So if you go very fast, if you would be able to go very fast at instantaneous measurement of the atmosphere and also instantaneous correction with a perfect deformable mirror, you would have TREL 1 and so the diffraction limit PSF. Since it is not the case, you have this fancy shape in which you have the diffraction limit PSF at the center. So it is composed by a core that is diffraction limit. And then you have a sort of dark zone in which the light is in fact all the light that was here went into the core, and then you have a big halo that has the size of the seeing, and that it contains all the light that has not been corrected by the system. It was very simplistic, but just to have an idea on what is happening. So you see here the profile, the typical profile, and how much this peak is high with respect to the halo depends on how much how well the correction has worked. So these are just an example of different PSF. So what is really frappante, I don't know how to say in English, but what you can see very easily is that these PSFs are very different one from the other, and they are very structured. So they present, some of them present structures, some of them less. All of these are real PSF, but one, maybe this one is simulated. All the others are extracted from real images of a different adaptive optics system. And this PSF is variable between during the night. Each night you have a different PSF because it depends how well the adaptive optics system has performed, and this depends also on the instantaneous turbulence. So this means that we have a problem. We don't know the PSF a priori, so we need to model it correctly. And why we need, we will see. Another thing that I want to say on adaptive optics is that I made a very simple example of one star, one deformable mirror, and correct, and that was really the classical, let's say, adaptive optics. In reality, now it exists a lot of different flavor of adaptive, different flavor of adaptive optics. The single conjugate adaptive optics is the one that I have cited before because it's the simplest scheme in which you have one star and one reference star, and you measure the turbulence in the direction of the reference star, and you apply to all the field of view this correction. And the effect that you have is that the correction is not homogeneous. So you have also variation of the PSF, and in the next slide we will see why. But then there are also other flavor exists, like multi-conjugate adaptive optics. It's a much more complicated scheme in which you use more than one star on the sky to map the atmosphere. So you can do a sort of 3D model of the atmosphere, and then using different, more than one deformable mirror, you can obtain finally an homogeneous correction of the atmosphere on a larger field of view, but at the price of a lower stress ratio. So depending really on the scientific case, you could be interested in one flavor or in another flavor. Why the PSF is variable across the field of view, and why in particular with this elongated shape that is pointing in the direction of the reference star. This is just really very basic. I don't want to go into equation, but I just would like to understand the concept at high level. No? So I have put here some turbulent screen, and then we have two footprints of in two directions, here and here. So let's suppose that we use the light coming from this direction to measure the turbulence, the atmospheric turbulence, and then we apply it to the DM, but we apply to all the field of view. So let's see what happens on the other side of the field of view, very far from the reference star. So the reference star is well corrected with the limits that we have said before. So the delay and then also the discretization. So it is not perfect, but it is the best that we can obtain. And that as soon as we go farther from the reference stars, the cylinder of atmosphere is not anymore identical. We can see here it's very similar but not identical. So what happens is that the correction is less good, and so the stress ratio goes down and the PSF is less corrected. And why is elongated? Very intuitively and not really correct example, but if you image again that these are the two footprints, and then you measure the atmosphere in the direction B, and you apply in the direction A, when you look from the top, okay, you have a representation from the top here, you can see that intuitively, the two footprints are more superimposed in one direction than in the other. So you have an effect of elongation of the PSF. So we have seen all the ingredients that I wanted to introduce today, and you knew maybe better than me some of them. So the fact is that the accurate knowledge and modeling of the PSF is crucial for the measurement of several key astronomical observables. In stellar fields, especially crowded stellar fields, an incorrect PSF modeling directly impacts both photometry and astrometry, and can even affect the source detection itself. So in this case, an accurate PSF model may lead to an underexploitation of the instrument potential, degrading the quality of the scientific results, and also the achievable performance. So it exists different approaches to model the PSF, ranging from purely analytical models that you know for sure very well, so using, for example, Moffat function, Gaussian function, or combination of them, or to fully empirical PSF modeling that I will show you later. So I will not say anything now. But another thing that is now coming out really is the reconstructed PSF. I will not talk about this in detail, but I will just say in a few words what is this. So you will hear about this in the future. And this is a very old concept that was published first time at the end of last century. And the idea was really to use, since you are using an adaptive optics system, you could save in some way all the telemetry, so all the data that are going around. So which are the commands that I apply to the DM, which are the measurements, and then using some statistics on atmosphere. And so to create a PSF that is completely theoretical, and it comes from the information that you have on the system and on the atmosphere in that moment. And this could be given with the corrected images from the instrument. So you would have received the image and the correlated PSF that has been computed in a theoretical way. This requires a lot of computation, a lot of memory. So this was not really used. It was only theoretical until 30 years ago, and now is becoming reality. So I will introduce quickly Starfinder. That is a software that has been written by Emiliano Diolaiti in 2000. So it's also something that is start to be very old, but it's been used a lot for adaptive optics images because it has been designed and sought for this purpose, and it uses a numerical PSF to make stellar field analysis, so astrometry and photometry. What does it mean, numerical or empirical PSF extraction? It means that instead of using a model or an analytical model or whatever, a model, you use the image of the star, so an array that you cut from your image, and you use the star as a PSF. And since you are affected by noise, of course, if you are using the image, you can take very bright images, but you have still the noise. So what you do is to choose a set of stars that are then averaged and used as a PSF. It is very simple. Then I have shown you that for adaptive optics, sometimes there is some variation of the PSF across the field of view. So how it is implemented in Starfinder, but also this is really the straightforward solution. You can consider that you can use this kind of model for the PSF even in fields where the PSF varies if you extract locally a set of stars and use a local PSF defining different subdomain in the image. So this is how Starfinder works. Now I just want to make you an example. So I've done a simulated image just to show you intuitively the possible impact on photometry and astrometry when you do not properly model the PSF, and how this could be treated in adaptive optics in particular. So this image has been simulated. The source comes from a catalog of stars that have a realistic range of magnitude distribution, and they are distributed in a small field of view, because we don't want to have too many stars. We just want to play a little bit with the simulation. Here you have the real PSF that has been used to create this image, and this PSF is a real PSF extracted from a real image. So then there is the noise and so on. So it's simulated images, but pretty realistic. And then here you have a PSF that I have created that is just a Gaussian, and this is the core of the PSF. So I'm not, now you don't see here very well, so I did also a logarithmic visualization, like this is a logarithmic visualization, so you can see clearly that the PSF is a complex structure with a big halo and diffraction-limited core. So the idea, and this is the difference between the a simple model, Gaussian model, that keeps only the core of the PSF and the entire PSF. So what I did was just to, I did the analysis of the field. So I computed, I did the detection. So I look at where are the stars, and then I measured the photometry and the position of the stars with Starfinder, but with another software is the same. And then I plotted this figure of merit. So this is the, sorry for the Italian here. This is the photometric error. Then we have the astrometric error and the completeness. The photometric error is gives you an idea on how much, how well I did the estimation of the flux. And this plot is possible because it's a simulated image. So I took the catalog that I used to create the image, and I made a comparison with the catalog that I obtained after the analysis of the image. And this is, I have plotted the difference between the two with respect to the magnitude, okay? And then this is the astrometric error that is the same, so I could make this plot because I have the original, the real position in pixel on the image. And the completeness just tell you also, you have the complete catalog in black, then in red you have in blue you have the stars that have been found by Starfinder, and in red the two ones. What means the two ones? That the green, that are the other, so 6 stars in this case have been detected and recognized, but in fact they were just noise or part of other PSF. So this is the case in which I have used the real PSF to do the analysis. And of course you have some error when you are at weak magnitude. So this is absolutely normal in a field analysis like this, because there are many magnitudes and the noise and so on. So what happens? I show you the animation. So what happens if I use a PSF that is not the good one? So I use only the core to do this exercise. So you can see clearly that there is a big error. There is an error that you do a photometric and an astrometric error that is due basically mainly to the fact that I'm not well estimated the halo, and so doing error in subtracting the contribution from other stars. And the interesting thing is also that if you remember, the green is also written here. The green histogram represents the false detections. So when you're not able to model properly the PSF in adaptive optics, one risk is that all these structures that secondary structure of the PSF could be taken, exchanged as sources. So these are spurious detected sources, and also these could contribute negatively to the estimation of the astrometry and photometry of the other stars. Another example, this is a real image. This is a real image taken with an MCAO system. And so it's a bigger, it's a 1 arc-minute field. Sorry, I forgot to put this information. And this time I don't want to look at the single photometric and astrometric error, because since it is a real image, I don't have the truth. The thing that you can use is the color magnitude diagram, that is in fact the plot of the magnitude in different bands, the difference of the magnitude in different bands. So the error, the photometric error, propagates also to this to the CMD, and you can see so the error that propagates. But I will show it in the next slide. So here, what I have done, since it is an adaptive optics image, I decided to check how much the impact of the variation of the PSF on the final results, so on the astrometry and the photometry. So I divided the field in different subdomains, and I extracted the PSF in each subdomain. It looks pretty constant, but if you could, you maybe see a small elongation in the corners. Anyway, When you do the analysis of the images in J and K band, you just show the K band, but when you do in the both band and then you build a CMD, you can clearly see if you use a single PSF, so you consider that the PSF doesn't change across the field of view, or you start to divide the image in different subdomains up to 7 by 7, you can clearly see that the CMD spread becomes smaller. So again, the message is do the best model of the PSF, and if you don't do it, even if you think that you have done it, you could have an impact on your final scientific results. The last example is an observation, again, a real observation done this year by, last year, by the group of Giuliana Fiorentino with the instrument ARIS the VLT, that is a single conjugate adaptive optics system that, as I said, I have said before, the single conjugate adaptive optics is characterized by a variable PSF across the field of view. So this time the exercise was a little bit different. So here you can see what happens if you use if you use an analytical model with a classical DAO program that has been not designed for this specific problem, or if you use Pathfinder, for example, that is being designed for adaptive optics and that takes into account variation of structure PSF, you can see that even if also this is not maybe a very good result in the sense that the image was not, the seeing that night was not very good, but you can clearly see how much you could improve your result. In particular here, this is the CMD related to the stars really at the center of the field, close to the PSF, close to the guide stars, so in which you have really the best correction, and so you have the less spread of the CMD. Just quick summarize up to here, so I have still 10 minutes to speak about our projects. So the PSF is the responsible system to a point source, you knew. The adaptive optics becomes necessary at this time, a necessary technology to recover the angular resolution of big telescopes because of the presence of atmosphere that degrade this angular resolution, but it produces complex PSF that could represent a difficulty and could vary also across the field of view. And to know the PSF to know properly the PSF is necessary for the data exploitation, for the proper data exploitation. So I will speak about this project, the Starfinder project. I say I have really not a name because since it's been financed in different frameworks, it has different names in different frameworks, but it is based on 3 main pillars. No? The first is a software development, fair software development. So there is a big work on code optimization because we are going in the direction of the ELT, so big images, and we need really to take a look at this kind of images, because of what I didn't say is that the analytical codes, the analytical PSF codes based on analytical PSF are for sure the fastest, because when you have to deal with a numerical PSF, you have arrays, basically, and so it could be very difficult to work with very big images. So there is a bigger work of code optimization in order to deal with this kind of images, and a big work of translation in Python, because the original code was written in IDL, and now in a few weeks you will have access to the Python code, and with a very nice GUI, so graphical interface based on client-server approach. Then another pillar is massive science data exploitation. This will started only for the verification part, but will be really the main character in the next years when the program will be released. And then another important branch is the fostering of future scientists and researchers through workshops dedicated to students. We have done PCTO high schools. Also because this tool, I'm so sorry that I can't show you. I have just a few images, but it's very, very nice also and didactic for school. So the economic context is the PNRR Styles project that has announced the core translation of Starfinder in Python, and then the PRIN 2022. The project is called Women Measuring Stars, and this project take with all the other aspects like didactic and also the science and the GUI part. Just one slide to say that we got a very nice experience with the students. In schools, we had a lot of meetings. We had a lot of hours with them, 40 hours. And we wanted to explain to them how much the software is important in astrophysics, and to go from images to real data, which is the path, real results, pardon, which is the path that where you have to go through. So the new Starfinder has been, so the Python version has not been developed internally, but we have decided to give this work to an external supplier, so an enterprise with an 18 months contract to a very nice enterprise that is Tega in Genova. We have executed the contract in 3 phases. One was mostly for to define the requirements that have been done together with scientists. Then the phase 2 was the core implementation, so the translation of Starfinder in Python, and the Python version that you can use from command line is still existing since a while. And then the last phase, that is the one that is going to finish in a couple of weeks, is the design and production of the GUI, so the graphical interface. To verify all the requirements, we have decided to go through define different use cases, and then to use as a comparison the ideal version of Starfinder. So we use different images, simulated and real, in order to see if the performance were maintained from the ideal version, because the development of the code, the optimization and so on has been done in EDL by me, Emiliano Diolaiti, and then translated literally from the external supplier. So which is the new modes you will find the Starfinder in Python in 2 configuration. You will be able to work into configuration, so with the command line and with the GUI. An interesting thing is that we have asked to implement also a third mode that is hybrid, so you will be able to use the GUI and then also to use to have access to the variables from the command line. So if you want to use your library, your favorite library, but in Python, but you also want to use the GUI, you will be able to do this. The user interface will be based on this server-client approach, and we'll use the browser. So it opens literally in a window of the browser. So you use the command line to launch it, and then one window of the browser opens, and the Starfinder is inside it. This is very nice because for the moment it's only for local use, but this is already thought and designed as if in the future could be implemented in pipelines of to be used remotely. So
Laura, you have 5 more minutes. Is that okay?
Yes, I am really at the end. So I would, at this point, I would have liked to use the program, but I don't know why I have to do the Windows update, and Visual Studio Code is not anymore working, and Python, I don't know, I have to check. So fortunately, I did some screen screen shot. So you can see here Starfinder open in one window of the browser. So you have the browser here with everything open, and then it opens in one of the window, and then this is how it looks like. You have 4 panels: image, PSF, astrometry, and photometry, and tools. And in the image panel, you can select an image in your computer and then upload it here. Now, since I can't, this is just an image, I can't show you, but this is really like a GS9, so you can really zoom with your mouse and change the color scale as you want. And then here you have a field vision with the zoom, and here in this part you have the zoom of the part that you are looking at. In this part, you have some info. So where you are passing, when you pass through with your mouse, you see the coordinates X and Y in pixels. And if the WCS are available, you can see also Rhine-Deck. Then you have the flux, the information, and you can read also the header from here. Then you upload the background noise. The background and noise, you can also compute them with this program or upload. You have the choice. And you can also, this is also a new feature of Starfinder, you can also define a mask in order to mask saturated images or whatever, saturated stars or whatever you want to mask. Then up, you have the PSF tab, which you can see the PSF, so you can upload the PSF, but you can also define. There is a fixed, but you can choose between fixed, variable, as I have said, and another kind that is a pre-interpolated PSF. That is a mode that has been developed for very big images. So in this case, you can save some computation time in pre-computing the PSF shifted on the pixel, so that you don't need to do this operation every time the software finds the star and try to fit the better position. So you do it once, and then the program just go to find the layer in the cube that correspond to the good shift. Here you can see how you can, the PSF can be built automatically by giving just the threshold and saying, and the number of stars you want to use to compute the PSF, or you can click literally in the image and choose the stars that you want to use for the PSF, the primary stars, and if you want to eliminate secondary stars, you can do it manually or automatically. This is the example in the case of the variable PSF. So you have different subdomains, and you can click in each subdomains to define the PSF, or Starfinder can do it automatically, but it's not always the good choice. I mean, you can choose, and then you can choose different geometry. So this is the most simple, in which the subdomains are just rectangular and with the same surface, but you can also move these lines and adapt as you want interactively the size. Then you can choose also fancy shapes for the definition. For example, this is a circular geometry that could be useful in case of elongation that point toward the reference star, and this point you can just move it, dragging with the mouse. And yes, here I have dragged some star with the mouse. You can even really define as you want the subdomains. Then the Starfinder, the third here, astrometry and photometry. I don't have an image in which you see the parameters, but you can set the usual parameters for astrometry and photometry, so the threshold and then other parameters. And you see as soon as you click the button run, it starts to work, and you have a time bar, so you know more or less where you are. And if you see that you have made an error, you can always stop it and change the parameters. You will not have to crash to stop Python. And then the last, this is really the last, what is, yes, you have a last tab that is called Tools. I'm so sorry that you can't see, but you can do first analysis of the image. There are a few very basic tools, like doing a plot across a certain line, or to do a color magnitude diagram. You don't see here, or some statistics. You can trace, you can select a zone in the image and do some statistics, like the average or the sigma and so on. So this could be useful also for the choice of the stars. And then you can also do aperture photometry. You don't see here, but you can see just a little bit aperture photometry. You can select some star and a circle around, and it does automatically the subtraction of the background in an annular part, so you can have an idea of the aperture photometry. And then here you have all the products available that you can see just clicking back. If you click on background, you see the image of the background, the image of the noise that is, if you don't consider photo noise, is the same number, so it's one value, and then you can see the PSF. And then these products are typical of Starfinder because, and how it works. So you build at the end a synthetic image because Starfinder put the PSF, scales it with flux that has been estimated, and shifted in the position that has been estimated. So finally you have really an image reconstructed from the analysis of the image, and you can do the residual by subtracting the one with respect to the other. So I think I have finished. I'm really sorry that I can't show you. I'm really disappointed. The idea was really to do this last part by uploading and running the code. And these are the acknowledgement that I'm obliged to show to you. And in general, if we are really at the end of this project in these days, in a couple of weeks, we will have the final product, but we will continue to test it. And I am really open, and every collaboration is very welcome. If some of us is interested in using this software, please contact me. And if you have some questions, please ask.
Thank you. Thank you. So if there are questions here or online, unmute yourself and ask the question now.
Okay.
Okay, now,
can you hear me?
Yeah.
Okay. Many thanks, Laura. It was a very clear presentation. I really appreciate you showed where you start, the issues, and the constraint, also technological constraint limitation that underlie this work. I just have a very simple question for you, just to know if Starfinder can also detect, or you plan to add some new functionality, like detecting non-point source or extended source in general to this analysis. And another point, if you plan to integrate some machine learning based functionality to your package.
Thank you, Gianluca. The first question is, both are very interesting, but the first one is funny because this kind of program, this kind of idea to use the image of the PSF and not a model or whatever, it is completely detached from the fact that it's a star, no? So it could be something else. You have to play a little bit with parameters, because, and for this reason, we decided some parameter that was not accessible to the user, not expert user, now could be accessible. So there are two modalities of working of the program. You can check the modality of expert, and so you have access of a lot to a lot of parameters, in which you can really may use this program to also with extended objects. I mean, I did use it to count bacteria in a colony. So really, you could use it for other even outside from astronomy. So, and I think that we have also used with a very defocused image with really when you are very defocused, you have a hole in the center, so you see really the pupil. It's not so easy, but if you become an expert, there is no function. But if you know how it works, you could use it for extended objects. It is not sought to find galaxies, but the problem is that it looks for a pattern that is the same. So you could set some parameter in order to find a certain pattern, not all the patterns that are familiar to this. I mean, if you change the size across the field, it doesn't work. Will never work. So this the answer to the first question is not only for stars, resolved stars, and so on, but you could in some way use it for other cases. Not all, doesn't do everything. It is very specialized on astrometry and photometry of stellar fields, with some possibility. Then the second question is about yes, it's very interesting, but it is not the approach of Starfinder. The approach, the nice thing is that Starfinder could compute the PSF, but the other thing is that accept an external PSF that has been needs just to be an image, and for the rest you can upload your PSF that you have computed with another software. So if in the future, apart from PSF reconstruction, this works with the reconstructed PSF. For example, if I have an image coming from a telescope and then they give me also the reconstructed PSF, I could use it in Starfinder. So it could be also a nice tool to test PSF reconstruction performance. But also, if you have, there will be at a certain point tools that use artificial intelligence to compute the PSF, and this will be compatible with the product, but is not able to, will never. Then it will be free. So if someone does something free, they could be, let's say, linked, but no, we don't do this. I don't know if there is some open, some nice. I think there is still no nice result on this kind of application.
Yeah, I'm asking because we very recently started work. Simone Sacquegna, maybe is linked or is in the room, is working to develop a machine learning based approach, let's say, to detect planets close to bright star using adaptive optics, and is using training is a network with a theoretical PSF. So I'm just wondering if we can use Starfinder to get, for example, LBT PSF. We are working with Fernando to check this instrument, so we can train the network with a more accurate PSF and then improve our. Also, this could be another way to see your work, the functionality of Starfinder.
Yes, for sure it is very useful as a testing tool for other way to estimate the PSF, because it's very versatile. So you just need to have a fixed or variable PSF. You give it like cube or like a single image. Then Starfinder, what it does, it's really in a very precise way astrometry and photometry. So then the rest, if the PSF comes from another tool, this is really a nice tool to make tests. So with your using come si dice, the test bed that you want to use, like the CMD, is a very nice merit function, because you can see the spread that goes with the precision of the PSF and so on, and also other kind of function merit function.
Other questions?
Yes, if I ask, I mean, you partially, can you hear me?
Yes.
Okay. You partially answered to when reply to Gianluca, but I was curious if you are not planning at this point to implement an hybrid approach, let's say, of construction PSF, because you mentioned that we are using a numerical approach, but you know that we are going in the hybrid mode.
But
like tip-top, other software.
Yes, but this would be so. The idea is this software is really not related to any instrument. You can use it.
Okay.
Really with the interface and the door not open more than often is the possibility to upload the PSF that you want. You just go to the PSF. It does not really need to be computed internally.
Okay.
So it has been done for this. And also, I would encourage people working on PSF, reconstructed PSF, to divulgate the interfaces. I mean, for the moment, I have no idea how they will be given, which will be the format fits file. There will be an header, more headers. There will be a cube with which kind of order, which will be the size. It will be needed to make a resampling, or it will be the final sampling. All this kind of information are very important in order to adapt the StarFinder to accept a PSF reconstructed. But then adapt the software with a lot of information, because to build an hybrid PSF, hybrid in the sense that you need the telemetry, becomes impossible, because telemetry
or maybe also analytical. Some analytical.
Also analytical, yes, there is the analytical. It's not in the GUI, but it's already present. I didn't mention. Yes, analytical is there, but it's a little bit more complicated to use. It's only from command line, and honestly, if it was only purely analytical, I would use maybe another software. Then there is also a possibility to use a hybrid PSF, and it is implemented also the model of PSF 2019, I think is the name, with NAILO, and that is, yes, it's an hybrid PSF between, in which you do an estimation of the halo through some data of the atmosphere, and then you do the rest from theory. And it's a little bit difficult to use, but if someone is interested, I'm absolutely available to explain how it works from command line. So this is coded inside, but not available from an easy interface.
Okay, thank you.
There is a question. Yeah, a question. Yes. Okay, there's a question from Mauro.
Ciao, Laura. It's Mauro.
Yeah.
Open fast question and the fast reply. When you showed the effects of PSF reconstruction on the astrophotometric error, you showed two diagrams.
Yes.
I noticed that while the astrometric error is plotted against the instrumental magnitude, the photometric one is plotted against the true magnitude.
No, true in the sense of...
just a case.
Sorry, it's always instrumental magnitude. True in the sense that it's the one that has been reported into the catalog, the input catalog. Let me...
Okay.
So this was instrumental. Both are instrumental, but it's wrong. Sorry. This is Vera in the sense true in the sense.
No, if
no, because minus 16. Yes, sorry. This is really a typo. I wanted to say
expression error in the budget.
Yes. No. It's instrumental, and it's the one of the input catalog.
Okay, thank you.
Laura, I have,
Yes.
I have many questions, but we don't have enough time. Do you hear me? Can you hear me?
Yes, not so good, but
Yeah, get closer. So I have many questions, but I'm going to ask just a couple. I'm very curious about using this tool, and I can't wait that is available. So I have a general question about AO, which is, so one of the key parameters is the fact that we do not have instantaneous correction, right? So what is the future for that? And what is the real limitation for that? Is it the analytical, so the analysis part to correct or the wavefront, that is the delay or the main cause for the delay, or is the mechanical part?
no,
You know?
it depends, really depends on, because I just introduced a very general concept.
I don't need the full answer. I'm curious about that.
No, it's just that there are different kind of adaptive optics.
Okay. And then the
so
other,
depending on the
yeah, no, I just we're randomly. The other question is: this tool only is mostly for to work with the AO system, or is it just for generic photometry?
No.
Or to using
generic for every kind of instrument. It has been used a lot for. I've just skipped some slides because it has been used a lot for instrumental from instruments for space instruments. Like I have used it and developed some tool for James Webb Space Telescope, or it has been used a lot for HST data because the PSF is structured, so it's exactly the kind of PSF that.
What is the advantage against what is the advantage against something like Sextractor or the wavefront? The main advantage.
Sextractor, you mean PSFX, or because Sextractor, I don't. I thought it was a Aperture PSFX. So the advantage, but there is if you. So I have never tried to extract a PSF with a Sextractor. We should see. But I think that for, correct me if I'm wrong, when you use instruments from like James Webb, you have already a PSF that is available. I have tried to do some reduction with this kind of images from JWST, and I could extract a very nice PSF, very detailed. Then, which is the best? I don't know. Never. This is not my job. So someone should try and see if there is an advantage or not in using something else. It has not been designed for this, but it can work very well also for JWST. I don't see any showstopper. It's just that it has not been used for JW, but for sure for HST there are many publications that have used this tool.
Okay, we have a network connection. Seems like is long, but anyways, thank you for the great talk. It was very clear, and Laura again.
Thank you.
Grazie, Laura.
And see you.
Ciao. And next talk will be next week by Umberto Battino, just in presence.